So hi everyone, my name is Elsa Tang and I'm currently a final year PhD student at UC San Diego, working with Professor Karen Sandstrom on molecular gas and star formation in nearby galaxies. So today I will be presenting a very new paper, which was just accepted by APJ last week, and it is already on arXiv and updated just a few days ago actually. So in this paper, we propose a new CO-to-H2 conversion factor prescription. And then based on the new prescription, we further investigate how such alpha CO variation would impact our knowledge of star formation efficiency across nearby galaxies. And this new prescription we propose is actually strongly motivated by our previous work. So in this talk, I will also briefly go through some of the key results from these papers where we have measured molecular gas properties and the conversion factor across several barred galaxy centers. And then I will also show how we identify the physical drivers and the key observables that can be used to trace the alpha CO variations. So our motivation is, of course, to study star formation in galaxies. And we know that stars are formed in molecular gas. So this means that star formation is controlled by both the amount of molecular gas and the efficiency of that gas being converted into stars. So these properties can be studied through the well-known molecular Kanneke-Schmidt relation, which, as you can see in these figures, that star formation rates are found to be tightly correlated with molecular gas surface density across a wide dynamic range. And so this relation has been laying an important foundation for many extragalactic star formation studies, because the roughly constant slopes here in these figures are basically suggesting that star formation efficiency is roughly consistent throughout different regions or different galaxies. However, to study either the molecular gas or star formation efficiency, we have to estimate the molecular gas mass. And unfortunately, the main component of molecular gas, which is the molecular hydrogen, it is not directly observable in the cold molecular gas. And so the standard way to trace molecular gas is to observe the CO emission and then apply a CO-to-H2 conversion factor, or alpha CO, so that we can derive the total H2 mass from the CO line flux. So you can think of this alpha CO as an empirical mass-to-light ratio, and previous studies have shown that this alpha CO is roughly around a constant of 4.4 throughout the Milky Way disk molecular clouds. And so many studies simply assume this constant alpha CO to derive molecular gas in different galaxies or different regions. However, alpha CO is not a simple constant because it does vary within and between galaxies. And also in theory, we know that alpha CO should depend on molecular gas properties like temperature, density, opacity, or metallicity. So for example, in this figure here, you can see that alpha CO can vary up to orders of magnitudes in different environments. And here I want to show that for very active galaxies like Euler's, they usually have lower conversion factor than the standard Milky Way value, because the gas in Euler's are often found to have higher temperature or turbulence that can increase the CO emission and decrease alpha CO. And even more interestingly, recent studies have also found that alpha CO is systematically lower towards the central kiloparsec of many normal star-forming galaxies. So it's possible that activities in galaxy centers like nuclear starbursts or even the gas inflows can also lead to extreme CO excitation or the dynamics that could also lower alpha CO value in these regions. So this finding makes galaxy centers become great targets to study the relation between molecular gas properties and alpha CO, because galaxy centers can be relatively nearby, but they also have spanned a wide range of environment conditions that could reach the extreme conditions as in Euler's. So now we see that alpha CO does vary a lot, but why is understanding this variation important? So we already showed that alpha CO is the basis of measuring molecular gas mass, and it is tied to the molecular gas conditions. But it is also important to realize that alpha CO not just impact the molecular gas mass, but also every star formation properties that are inferred from the molecular gas mass. So here I'm only listing a few critical parameters that have been widely used in current star formation studies. And you can see that all of them depends on the molecular gas mass. So this means that alpha CO can have great effects on estimating these important star formation properties. So as an example, here is a figure from Ellison et al. 2020. And this plot is trying to figure out whether the starbursts in galaxy centers are primarily driven by higher molecular gas mass fraction or higher star formation efficiency. But all these data points here you see were assumed to have a constant Milky Way alpha CO. So it looks like most of the data points aligns pretty well with this one-to-one relation line. And so this would suggest that molecular gas fraction and star formation efficiency contribute roughly equally to the high star formation rates. However, as you can see, both parameters should be very sensitive to the alpha CO change. So here from this green arrow, you can see that even with just a factor of 2 decrease of alpha CO, would move all these data points to the lower right fraction of this plot, which would suggest a totally different conclusion that star formation efficiency totally dominate over the molecular gas fraction. And here's another similar example, which studies the star formation efficiency per freefall time across a single galaxy. So the concept is similar, that if galaxy centers, which is this data point, if it actually has alpha CO that is a factor of few lower than the Milky Way, then it would be moved further away from this red line. And this would no longer suggest a constant star formation efficiency per freefall time. So these examples are just showing that using a wrong alpha CO can really bias the estimation of many important quantities. And actually nowadays, alpha CO variation has become the dominant source of uncertainty in molecular gas measurements. And so to break through this limitation, we have to understand how alpha CO behaves across different environment conditions. And then we can establish a robust alpha CO prescription to be applied across different galaxies. So this is why in our paper, we want to explore how our new alpha CO prescription would renew our understanding in the star formation efficiencies. But before showing our new prescription, let me give a bit background on how the prescription was motivated. So in our earlier work, we observed 3 nearby barred galaxies with multi-band CO isotopolog lines because these galaxies were suspected by previous lower resolution studies that they may have substantially lower alpha CO in their central kiloparsec. And so we used ALMA to observe 6 12CO, 13CO, and C18O lines towards the central 2 kiloparsec of these galaxies, which is the yellow boxes here. And for all 6 lines we observe, they reach an angular resolution of at least 100 parsec, which corresponds to the giant molecular cloud scales that is similar to the PHANGS resolution. And so to determine the physical conditions and alpha CO in different regions of these galaxies, we use non-LTE radiative transfer with Bayesian likelihood analysis to study the probability distributions of multiple parameters that are relevant to alpha CO variations. So this includes like CO opacity, temperature, density, and isotopolog abundance ratios. And then with these directly modeled parameters, we can further constrain alpha CO likelihoods in each pixel on our maps. So here you can see how our derived alpha CO varies with the galactocentric radius in all 3 galaxy centers. So it's clear that in all the three galaxies, our derived alpha CO are typically 5 to 15 times lower than the Milky Way alpha CO. And we even find that in specific regions, like the inflow arms driven, the inflow lanes driven by the bar at the NGC 3351 galaxy center, the alpha CO there can even reach like 30 to 40 times lower than the Milky Way value. And so after deriving alpha CO and various molecular gas properties, we move on to study their correlation and see what is driving the alpha CO in these regions. So first, we find that there is a very strong correlation between alpha CO and the CO optical depth in these optically thick regions. So this optically thick region basically covers all the pixels in these galaxy centers, except for the bar-driven inflow arms I showed for NGC 3351, which we found that they are optically thin. And so we find that this very tight correlation between alpha CO and tau CO can explain about 80% of the alpha CO variation across these galaxy centers. But also from the figure below, you can see that alpha CO also decreases with the kinetic temperature, which also makes sense because higher temperature should also increase the CO emission and decrease alpha CO. But it's clear that the scatter here in the temperature relation are much larger than the scatter in the optical depth relation. So it's clear that optical depth effects are more dominant in driving alpha CO variation in these regions. So now knowing that, that alpha CO is mainly driven by optical depth, our next step was to think if we can identify any observational tracers that can trace optical depth so that we could further use it to trace the alpha CO trend. So if you recall, in our earlier 2022 paper, we targeted only NGC 3351, and there we observed significantly higher CO to 13 CO line ratio in the gas inflow arms, and also a substantially larger line width in the inflows. So I also showed that these inflow arms have substantially lower alpha CO and optical depth, because you can see that that region is the only region with optically thin molecular gas. So we think this is suggesting that the low alpha CO is caused by the increased CO emission due to the very low CO optical depth. And this would perfectly explain this scenario because you can imagine that larger line width would reduce the CO optical depth and lead to increased CO emission that cause this high line ratio we see. However, this is only one galaxy, but an even more exciting result is that when we combine all three galaxy centers, we do see a clear trend that alpha CO decreases with both the CO to 13 CO line ratio and the CO line width. And so this means that both observables can be useful to trace alpha CO variations because of their relation with the CO optical depth, which is the main driver of alpha CO. But now the next question is whether we can verify these relations on a larger sample of galaxies. So as you can see, currently we only have complete isotopolog data set on 3 galaxy centers. And this is because high resolution observations of multiple CO isotopologs are really expensive. So another option we have is to switch to dust-based alpha CO, which is typically at much lower resolution than the CO observations, but we can still test if these relations we found based on CO isotopologs would also work on the dust measurements across a larger sample of galaxies. And it turns out that the line width dependence does work on more galaxies. So here, the blue line and the blue shaded area here are recent dust-based alpha CO measurements, and they are correlated with the 150 parsec scale velocity dispersion from the PHANGS dataset. So this whole data covers 12 barred and non-barred galaxies out to a galactocentric radius of 10 kiloparsec. So you can see that this the trend of this data aligns very well with this orange dashed line here, which is the relation we saw on the 3 barred galaxy centers. So it was really encouraging to see that this relation not only holds for barred galaxy centers, but also for non-barred galaxies and even out to the disk regions. So based on these measurements, we have constructed a new alpha CO prescription as a function of cloud scale velocity dispersion. And as you can see, the data scatter in our prescription is only about 0.1 dex. So this is the smallest scatter among existing alpha CO prescriptions. And we think this is because the velocity dispersion here are directly tracing the physics that alters alpha CO, which is the optical depth variations. And also another unique advantage of our prescription is that it requires only the CO observations that is most relevant to tracing the molecular gas, so that the CO data itself will be enough to predict alpha CO. And another interesting thing we also discuss in our paper is that we find the velocity dispersion here may also reflect the trend of other correlated properties. So for example, we know that metallicity may also drive alpha CO variations. And so here we also explore how the dust-based alpha CO vary with metallicity. So you can see that alpha CO does decrease with metallicity, and the trend is actually quite consistent with the Eckersole et al. 2017 prescription, which is the typically used prescription in the PHANGS work. But it is also clear that the scatter here is much larger than our prescription with the velocity dispersion. And so furthermore, we want to know if the residual from our prescription can be explained by the metallicity variations. So in the bottom panels here, we correlate our residuals from the top panels with metallicity, and we do the same for the metallicity fits to correlate with velocity dispersion. So you can see that the residual from our prescription has almost no trend with metallicity, but the residual from the metallicity fit clearly varies with the velocity dispersion. And so this means that the alpha CO variation with metallicity is somehow already included in this trend with velocity dispersion. So that's why our prescription does not need additional metallicity term. And we have checked that this is because velocity dispersion and metallicity are correlated, probably because they both vary with the galactocentric radius. And so this may also explain why our velocity dispersion prescription can work so well across the entire galaxy disks. And finally, we want to investigate how these alpha CO variation would impact the star formation efficiency across nearby galaxies. So we do this by applying our prescription to 65 galaxies from PHANGS, and then we see how the derived Kaneka-Schmidt distribution would differ from using Milky Way alpha CO. So from these figures, it's very clear that our prescription reveals higher star formation efficiency towards galaxy centers, but the Milky Way alpha CO, in contrast, it suggests a roughly consistent star formation efficiency across both regions. And also, if you compare the exact values of molecular gas mass, you will see that the molecular gas surface density can be overestimated by a factor of 5 if we use a Milky Way alpha CO. And even further, we want to separate barred and non-barred galaxies and compare the derived molecular gas depletion time using different alpha CO prescriptions. So this includes using Milky Way alpha CO, metallicity-based alpha CO, and the Bellotto 2013 prescription, and also, of course, our new prescription. So first of all, we find that in galaxy disks, all the prescription leads to similar depletion time distribution, regardless of it is barred or non-barred galaxies. But interestingly, when we go into galaxy centers, it is now clear that both Milky Way alpha CO and metallicity-based alpha CO give a longer depletion time that can be 3 to 5 times longer than using our prescription or the Bellotto prescription. And also, even though the Bellotto 13 prescription predicts shorter depletion time in general, and the average is actually similar to our Galaxy Center average, but we find that only our prescription reveals shorter depletion time in barred galaxy centers. That you can see there's a clear separation that indicates a factor of 3 difference in the median values. So this means that the star formation efficiency in barred galaxy centers is somehow enhanced. And we think this can affect our current knowledge of molecular gas concentration in galaxy centers, because previous studies using a Milky Way alpha CO, they reported a higher amount of molecular gas in barred galaxy centers. And so they use this to explain why star formation rates are found to be higher. Because if you can imagine that if star formation efficiency is constant, then higher molecular gas mass should result in higher star formation rates. But with our prescription, we actually find that the molecular gas mass is similar between barred and non-barred galaxy centers. So it's possible that the high star formation rates in barred centers are instead caused by a higher star formation efficiency rather than the higher amount of molecular gas mass. And so one of our future direction is to answer what is driving this star formation efficiency enhancement in these barred galaxy centers. Because the interesting thing here is that the factors driving star formation efficiency, like the gas structure, density, or dynamical effects, these are the same conditions that would alter the alpha CO values. And so only when we have the correct alpha CO, we can move on to study the true variation of star formation efficiency. And I think now is especially a good time to study star formation efficiency, because with JWST, we can now probe into the warm molecular gas through direct detection of H2 rotational ladders, just like this recent studies from Hernandez et al. They detect 7 H2 rotational lines in the center of M83. And so this kind of study would allow us to understand the influence of stellar feedback process on star formation efficiency. So I will stop my talk here, and here is my key takeaway messages, and I'm happy to take questions. Thank you very much.